All right. Thanks for the very good questions in the break. And now I have one for you. Namely, so we have seen this very special construction. We have seen this weird construction of the coupling network. The main purpose was to guarantee invertibility. And this invertibility is exact. Yeah, it's perfect. And I wanted to ask you if you have an idea how to replace this exact invertibility by something approximate, where we can use, then we would have two kinds of losses. We would have one kind of loss to maximize the likelihood as before, and we would have a second kind of loss to at least approximate this, to make sure we have at least approximate invertibility. Do you have ideas on how to do that? I'll give you a moment. Does it ring any bell? Okay. So the suggestion was to use an autoencoder, and because in autoencoders, so the way we have normally plotted them was to say, all right, we have here our input. Okay, let me start the other way around this time. We have our target distribution X, and we can put this into an encoder, and we get out a Z, and then we could put this into a decoder and obtain an X tilde. And then we can have a reconstruction loss which says that X minus X tilde should please be small. Then we have an well, a consistent autoencoder. And in the coupling networks, the encoder and the decoder, they were identical. They were just flipped. Yeah? So in the coupling networks, we had X, and then we had our invertible neural network. So X went into the invertible neural network to give me Z, and I could put Z into the invertible neural network to get back X. So another way to plot this is to say I put X into my invertible neural network to get Z, and then I put that into my invertible neural network, which is flipped. I'm writing here -1, and then I get X tilde, which is identical to X, because this is an invertible neural network. Yeah, so these two architectures are the same. And this is what you have just proposed. Yeah? And now let's discuss the question of the dimensions here. Normally, when we talk about autoencoders, we always said we start with a high-dimensional space and we go to a low-dimensional space, and then we inflate this back to high-dimensional space. But this time, at least usually, the base distribution and the target distribution, they have the same dimensionality. Yeah? So this would be an autoencoder without a bottleneck dimension or a full-dimensional autoencoder. Yeah? And indeed, this is a very nice idea that has been developed here in Heidelberg in the lab of Ulrich Köthe. So Felix Draxler and Peter Sorensen have explored this idea under the title of free-form flows. Yeah, and this is the basic idea. And now the downside is that it's not precisely invertible, it's only approximate. And the upside is that you don't have these weird architectural constraints that we have seen in the coupling neural networks. Okay, but I now want to come to the next class of architectures. Yes? Should variation autoencoders not be much better? Why? You mean yeah, so I think if you use standard regularization techniques on the encoder and the decoder network, it will be you will get smoothness implicitly. Yeah? All right. So here is a famous picture from the paper on neural ordinary differential equations. And we see on the left-hand side what a typical invertible neural network approach would do. So here we would have 5 layers. And we have seen that in the coupling flows, each layer did something very simple. Yeah? Each layer did a scaling and shifting for a subset of the dimensions. Now here, the thing with multiple dimensions is difficult to draw. So here we have an example where we have a one-dimensional base distribution, a one-dimensional target distribution, and from bottom to top are the layers, or if you wish, a discrete approximation to time. And shown here is this mapping F, which each and every one of the layers performs. And I previously had this picture on the board where I said, well, we can have more general flows. Yeah? And in ordinary, in neural ODE Ansätzen, what you do is that you model with a neural network this underlying flow field. Yeah? So this flow field, you now make time continuous, and you say that my neural network models the entire flow field. And then I can integrate motions here. And now I'm not restricted to do this at equidistant times, but I can use an off-the-shelf ODE solver and sample this underlying flow field at arbitrary times. Yeah, so here you see this was always at the same time, at the same time, at the same time. And here, depending on how strongly curved, this is now a cartoon, but depending on, for example, on how strongly curved this trajectory is, the ODE solver can decide to use more or less sample points along the trajectory. And so this would be a kind of primitive Euler integrator, and this would be a more general, fancier integrator that's used here. So that's the basic idea behind neural ODEs. And let's look at them in a bit more detail. So one perspective is to say that these are continuous normalizing flows, where continuous now means in the time dimension. So do you have a particular question, anything you would like to discuss? Thank you. So we assume that we distort the space variable z over time. So this is a random variable with some probability. So this random variable now changes its distribution with time, and this change with time is modeled by a neural network. And this neural network will do different things, or this flow field will change for different times. And this induces a probability flow, or a flow of probability mass. And this probability flow obeys the continuity equation. The continuity equation is known, you will have seen this in fluid dynamics, for example, where it guarantees preservation of mass. And so the change in probability is given by minus here this divergence of the probability mass flux. So we have P of z of t times f of z of t and t. So probability, I'm putting mass in quotes here. And if we multiply this out, we get two contributions here. We have, on the one hand, the probability weighted divergence of the flow. And we have, on the other hand, here by the product rule, the gradient of the probability density. And this term here gives me the advection or the transport of the probability mass of this flow. And previously we had discrete layers and a change of variables in each of these layers. And we now have something that's sometimes called the instantaneous change of variables. So d of logarithm of this probability is minus the trace of the Jacobian. And this trace here is somewhat easier to compute than the determinant, which we had previously. We had an expression with a determinant. And even the expressions involving determinants are relatively efficient in these invertible neural networks because they are designed so as to have for example, lower triangular Jacobians, in which then the determinant is also just a product of the diagonal entries. But still, for the trace, there is a trick, the Hutchinson trace estimator, which allows computing this really efficiently. Okay, and so in this case, one can again maximize the log likelihood, but this time the network models this flow as a continuous function. Yeah, so it's a function of both the original coordinates and an extra time dimension. And in flow matching, the idea is to no longer backprop through this kind of transport, but in flow matching, the idea is to directly train the drift term. And so flow matching is yet another technique in this growing family of flow-based models. It directly learns the drift term, and this makes it relatively similar to diffusion models. And this flow matching is very similar to the rectified flows. And the paper I showed at the beginning of today, that used rectified flows. And now the question is, which flow should we use? And you remember the many pictures I draw at the beginning of today. We showed many legit flows, but which one should one use? And there are many good things to say about the simplest possible flows, which are the optimal transport-based ones. So OT for optimal transport. Based flows. And these are the final ones that I want to mention today. In one dimension, we saw that finding the optimal transport was very simple. We computed the cumulative distribution function and plotted those against each other. And in this way, we obtained the perfect mapping in one dimension. And in multiple dimensions, unfortunately, this is not so easy. So here I have, some probability density function. I have some points sampled from it. Here I've rotated the probability density function a little bit. Those are the same points rotated. And on the top right are now the cumulative distribution functions. And you see the PDF has just rotated, but the CDF, the cumulative distribution function, it has really changed qualitatively. So in a single dimension, there is just, if I want to compute the cumulative distribution function, there's just the arbitrary choice of, do I want to integrate from -infinity or to +infinity? But once we've made this choice, the CDF in one dimension is uniquely determined. And here in multiple dimensions, I need to choose a coordinate system. And the original coordinate system might be somewhat arbitrary. And now as I change my probability density, my CDF does not just rotate, it really changes in shape. Yeah, it really changes fundamentally. And so, unfortunately, in multiple dimensions, we cannot just in multiple dimensions, we cannot simply use the solution we had from 1D to find optimal transport. Instead, we really need to find this optimal mapping. And to find this optimal mapping, I want to give you 3 different formulations, and only the first of these we had seen last time. Now, if we want to use optimal transport, we need to pick a cost function. And the most typical cost functions are the Euclidean distance for the transport of probability mass, or the squared Euclidean distance. And in particular, the squared Euclidean distance is the most popular one. I'm going to write here penalize a probability mass transport with the squared Euclidean distance. But the fact that we use the squared Euclidean distance is arbitrary. I do it because the last of the 3 formulations that I give will only be possible with this squared Euclidean distance. And the first formulation I want to give is the Monge formulation. And this is useful whenever a deterministic transport map can be found. And I'm writing now W for Wasserstein, 2 because it's the squared Euclidean distance, and I'm squaring it so that I don't need to write a square root. And if I now have 2 distributions here, a base distribution and a target distribution, and I want to know what's the Wasserstein 2 distance, if I want to parameterize this explicitly with time, I will say that I'm going to use Z for, I can index the distribution of my random variable with time itself. So at t equals 0, we are at the base distribution. At t equals 1, we are at the target distribution. And this now looks for the best transport map. So this hash here is the transport map that pushes forward my base distribution to my target distribution. And then I ask for each point in my base distribution, how far is it in squared Euclidean distance from where it's being mapped? And I weight this with the probability of this base distribution. And if we minimize this, if we find the best transport map, that gives me in 1D exactly the solutions we had discussed as optimal transport solutions. But sometimes a deterministic transport map does not exist. And in that case, we need the Kantorovich formulation. And I mentioned an example briefly. If in my base distribution I have just a single piece of probability mass, but if in the target distribution I have 2 peaks of probability mass, then, well, I need to send a little bit here and a little bit there. And so I no longer have a one-to-one and onto mapping. I don't have a bijection anymore. And in this case, I can still find the best possible non-deterministic transport plan. And this plan is given in terms of a coupling. So the Wasserstein-2 distance squared between PZ and PX is now given as the best possible coupling pi. Which must be from the family of admissible couplings. It's all those that have the correct marginal distributions PZ and PX. And the integral now goes over the product space and well, evaluates this squared Euclidean distance under this measure here. And so these two formulations, they work for any choice. I can take the Euclidean distance or the squared Euclidean distance or anything else. But the following formulation that I want to talk about now only works for the case of the squared Euclidean distance. This picture here is from a really nice book, Computational Optimal Transport by Perret and Couturi. We see two examples. So a base distribution in red, a target distribution in blue. And on the left-hand side, a deterministic mapping is possible. So each of these points has unit mass. And for each of the points, it's cheapest to send it to one particular other partner. Here, the points have different probability mass as indicated by the radius of those circles. And here you see it's no longer a bijection. Sometimes mass from one point must be transported to two other points. And there is now a third formulation for the squared Euclidean distance, namely a so-called dynamic formulation. And here we parameterize by time from 0 to 1 this motion. And as I go from 0 to 1, for example, this point here moves very little, while the other one moves fast. Yeah? So this one has to cover a short distance, that one has to cover a long distance. So as t goes from 0 to 1, this one will move a lot further than that one. And in optimal transport, these connections are always straight lines. And this Benamou-Brenier formulation, or dynamic optimal transport formulation, looks at the velocity of, or at the kinetic energy of my entire probability mass and minimizes that. So Benamou-Brenier, also known as dynamic optimal transport formulation. It looks again at this squared Wasserstein-2 distance and at the probability. Now I'm using this parameterization with time here, the PDF over the random variable z, whose distribution changes with time. And this is now defined as the infimum over my intermediate probabilities and my flow field, such that when I integrate over time and when I integrate the squared velocity, so this is my flow field, and I square it. I weight it with the probability density at that time. And now I must make sure that no mass is lost, because otherwise it could just decide to set the intermediate probabilities to 0. So I need to enforce the continuity equation. I need to say such that dp by dt is minus the divergence here of p times f. All right, and what we find here is the minimal kinetic energy of the probability flow, that actually translates my base distribution into my target distribution. All right. And this is an idea or a formulation that is also starting to be used in flow-based models. In particular, there is the paper on optimal transport conditional flow matching. And thanks again to Peter for pointing that one out. One of the authors is Guy Wolf, who was a Humboldt visiting fellow in our lab for 6 months last year. And the paper is called something like Improving Flow-Based something with mini-batch optimal transport. And the basic approach is the following. If we have a training sample for which we want to learn the flow, we compute the approximate optimal transport, and then use this Benamou-Brenier. We use the dynamic OT formulation. So in other words, once I have decided that by solving the optimal transport problem, that this point from my base distribution maps here, and that point from my base distribution maps there, I can now parameterize it by time. Yeah, as time goes from 0 to 1, this one moves only so far, that one moves so far. And then I fit, using a neural network, this displacement field. So these samples now really are here in my p-dimensional space. Yeah, this is the p-dimensional space in which my training samples live. And then a neural network displacement field is fitted to this optimal one. So I fit this to the Benamou-Brenier displacement field by simply minimizing the square loss. So in this p-dimensional space, I have a sample, I have a training set of target samples. I have my base distribution, which could be Gaussian or something more complicated. I solve the optimal transport problem. Doing this exactly in high dimensional data is expensive. So here an approximation is used to do this only on mini batches. We get out a displacement field, and we imitate this displacement field using a neural network. And this has advantages and disadvantages. So the advantage is that this, once it's trained, this allows a single-step synthesis. And another advantage is that we have these very simple flow patterns. Yeah, we have the straight paths. And we have, we feel morally superior because we do optimal transport. Do you have any arguments of what could make this difficult? If we think about problems like image synthesis. So in image synthesis, let's say I just want to synthesize natural looking images. Yeah? I can either do this really in the space of all pixels, then RP is, then P is 1,000,000 dimensions, or I can do this in a lower dimensional latent space. But even so, my natural images, they live on a low dimensional manifold. And I now have some starting distribution, maybe a Gaussian-based distribution. What could be difficult if I try and use this approach? Yes? Sorry. It could be degenerate, mode collapse, and so on, I think you're suggesting, yes? Do you have other ideas of what could make this difficult? Well, yes, it requires many parameters. I think the advantage, the disadvantage or the problem is, again, that it's a single step method. Yeah? So because once we have trained this, we say, talking about images, let's say we operate in this 1,000,000 dimensional space of pixels. We sample just a noise image, a pure random image. And then our model must be able in a single step to say, in which direction must I walk and how far to obtain a perfect, real looking, natural looking image. That's a whole lot to ask of a model. And normally, I would say it's not possible, but let's wait, as more training data comes along. Yeah? So right now, the sweet spot for simulating really complex samples seem to be models where the neural network doesn't have to do it in a single shot, but where the neural network does have multiple iterations. And the paper I showed at the outset today was this here, rectified flows, which uses not straight, but it uses curved trajectories and invokes a neural network more often. Yeah, so it's slower at test time. Is that right? Is it, do you know, Peter, does it do curved trajectories or not? The rectified flows? Thanks to my joker. So they penalize, and some papers do this explicitly, to penalize curved trajectories, but they're not single-step synthesis methods. Okay, good. So this lecture was still a bit rough around the edges. As the textbook, and that's because some of the material is fairly new. So the best textbook I would recommend today for this is Bishop, but Bishop really only covers what we discussed today up to neural ODEs, and the optimal transport part has not made it to the textbooks yet. And I'm very curious to see in 2 years' time. You know, in the end, I hope optimal transport wins. Let's see in 2 years' time if this is true or not. Yeah, other than that, thanks for your patience with a lecture that I'm sure in 2 years will be more mature. On Thursday this week, we will go away from pure generative AI and turn to more interesting structured data, namely to graphs. We will discuss graph neural networks, and there will be a bit of a non-religious Christmas touch to the lecture also. See you on Thursday.